Hello, hello all. Today's topic of lecture is complex variable part 1, that is complex number. I am SR Gaikwad, assistant professor in Department of Mathematics. Please subscribe my YouTube channel Parisram Maths Academy. Now the first topic is complex number. Definition of complex number. A number of the type z equal to x plus iy, where x and y are real number and I equal to root of minus 1 is called as complex number. That is a number of the type z equal to x plus iy. Here x and y both are real number. This type of number is called as a complex number. Now, if z equal to x plus iy is a complex number, then x is called real part of complex number z, y is called imaginary part of complex number z, and I equal to root of minus 1 is called as a imaginary number. Now I equal to root of minus 1, squaring on both sides, we get I square equal to minus 1. Multiply left hand side and right hand side by I, we get I cube equal to minus I. Again multiply left hand side and right hand side by I, we get I raised to 4 is same as minus I square, but value of I square is minus 1, therefore I raised to 4 is same as 1. Then 1 upon I, we can multiply and divide by I, we get I upon I square, but value of I square is minus 1, and therefore the value of 1 upon I is minus I. Now I raised to 4 equal to 1, then I raised to n equal to 1 if n is multiple of 4, that is power of I is multiple of 4, then value of I raised to n is 1. Next, complex conjugate definition. Let z equal to x plus iy be a complex number. The complex conjugate of z is denoted by z bar and defined as z bar equal to x minus iy. It means if z equal to x plus iy is complex number, then complex conjugate nothing but z bar equal to x minus iy. For example, if z equal to 2 plus 3i, then value of z bar is 2 minus 3i. If z equal to 4 minus 3i, then z bar equal to 4 plus 3i. If z equal to 7i, then z bar equal to minus 7i. If z equal to 5, then z bar equal to also 5. It means if z is purely real, then value of z is same as z bar. Now, z equal to x plus iy, z bar equal to x minus iy, then addition of z and z bar, that is z plus z bar equal to twice x. It appear plus iy minus iy cancel, it means z plus z bar equal to twice x. By taking their subtraction, z minus z bar equal to here plus, the plusing this minus x cancel, we get 2 iy. It means z minus z bar equal to 2 iy. Now, z plus z bar equal to twice x, and therefore z plus z bar upon 2 equal to x, z minus z bar upon 2 equal to iy, and z minus z bar upon twice I is same as y. Now, modulus of complex number definition. Let z equal to x plus iy is a complex number. The modulus of complex number z is denoted by mod z and defined as mod of z equal to root of x square plus y square. That is, if z equal to x plus iy, then modulus of z nothing but mod of z nothing but root of square of real part plus square of imaginary part. And therefore, if z equal to x plus iy, then mod of z equal to root of x square plus y square, and squaring on both sides, mod of z square equal to x square plus y square. Now, let we can take z equal to x plus y is complex number. Value of z bar is x minus iy, and therefore the product z into z bar equal to z is x plus iy, z bar is x minus iy. Taking their usual product, we get x square minus I into xy plus I into xy, last minus I square into y square. Middle two terms are same, they are cancelled. Value of I square is minus 1, and the last term is minus minus plus, and that is equal to x square plus y square. But x square plus y square equal to mod of z square, and therefore z into z bar equal to mod of z square. And therefore we get the result z nothing but x plus iy, z bar equal to x minus iy equal to mod of z square means x square plus y square, which is standard result. X plus iy into x minus iy equal to x square plus y square. Then amplitude of complex number. Let z equal to x plus iy is a complex number. The complex number z represent a point p in bracket x comma y in xy plane. That is complex number represent a point. We can consider the figure plane coordinate system. This x-axis, y-axis. Here x-axis is called as a real axis, y-axis is called as a imaginary axis. The point P in bracket x comma y represent complex number x plus iy. From point P, you can draw the line perpendicular on x-axis. We get this right angle triangle. Suppose this angle is theta. It means line OP make an angle theta with x-axis. And suppose distance OP is r. And therefore, from this right angle triangle, we get value of cos theta nothing but opposite side upon hypotenuse, that is x upon r. Value of sin theta is value of cos theta is adjacent side upon hypotenuse. It means cos theta equal to x upon r, and value of sin theta nothing but opposite side upon hypotenuse, that is y upon r. It means x equal to r cos theta, y equal to r sin theta. And therefore, z equal to x plus iy is a complex number in Cartesian form. But value of x is r cos theta, value of y is r sin theta, and therefore z equal to r cos theta plus I times r sin theta. By taking r as common, we get r in bracket cos theta plus I times sin theta. This type of form is called as a complex number in polar form. Here r and theta nothing but polar coordinate. Now, we know that cos theta plus I times sin of theta nothing but e raised to I theta, and therefore z equal to r in bracket cos theta plus I sin theta can be expressed as z equal to r into e raised to I theta, and this form nothing but complex number in exponential form. There are three forms of complex number. First, Cartesian form nothing but x plus iy, z equal to r in bracket cos theta plus I sin theta nothing but polar form, and z equal to r into e raised to I theta is complex number in exponential form. Now, x equal to r cos theta, y equal to r sin theta, and therefore x square plus y square, value of x square is r square cos square theta, value of y square is r square sin square theta. By taking r square as common, value of cos square theta plus sin square theta is 1, and therefore value of x square plus y square equal to r square. And therefore, mod of z equal to value of mod of z nothing but root of x square plus y square, and this root of x square plus y square is same as r. And from the value of sin theta and cos theta, we get tan of theta equal to y upon x, and therefore the value of theta is tan inverse of y upon x, and therefore we get the result modulus of z equal to mod of z, which equal to r equal to root of x square plus y square, and amplitude of z equal denoted by amp of z nothing but theta equal to tan inverse of y upon x. It is also called as a argument of z, and therefore r nothing but root x square plus y square, and theta nothing but tan inverse of y upon x. These are relation between Cartesian and polar coordinate. Then we can take some examples. First example, express the following complex number in polar form. First example, we can take 1 plus I. 1 plus I is complex number in Cartesian form. We can express this complex number in polar form. Solution. Let z equal to 1 plus I. We can compare this complex number with x plus iy, and therefore x equal to 1, y equal to 1, and therefore r equal to root of x square plus y square. Value of x is 1, value of y is 1, therefore root of 1 plus 1, that is root of 2. It means r equal to root of 2. And theta equal to tan inverse of y upon x equal to tan inverse of value of y is 1 upon value of x is 1, that is tan inverse of 1, value of tan inverse of 1 is pi by 4, and therefore z equal to r in bracket cos theta plus I times sin of theta. Value of r is root of 2, and value of theta is pi by 4, and therefore z equal to root of 2 into cos pi by 4 plus I times sin pi by 4 is a complex number in polar form. Okay. Next example, 1 minus I into root of 3. This complex number in Cartesian form. Solution. At z equal to 1 minus I root 3, comparing we get x equal to 1, y equal to minus root of 3. And therefore r equal to root of x square plus y square. Value of x is 1, value of y is root of 3. It means value of y square is 3. That's root of 1 plus 3. It means root of 4. That is 2. It means value of r is 2. And theta equal to tan inverse of y upon x equal to tan inverse of value of y is minus root 3 upon value of x is 1, that is tan inverse of minus root of 3. Here x is positive, y is negative. It means point P in bracket x comma y lies in fourth quadrant. Therefore angle lies in fourth quadrant. Therefore angle is 5 pi upon 3. And therefore z equal to r into cos theta plus I times sine of theta. Value of r is 2. Value of theta is 5 pi upon 3. And therefore z equal to 2 into cos 5 pi by 3 plus I times sine pi by 3 is complex number in polar form. Next. Third example. 1 minus I upon 1 plus I. Solution. Let z equal to 1 minus I upon 1 plus I. First you can simplify. You can express this complex number in the form x plus iy. For this we can multiply and divide by complex conjugate of denominator, that is multiply and divide by 1 minus I, and then simply we get 1 minus I into 1 minus I. Taking the usual product we get 1 minus I minus I, last term is minus minus plus I square, value of I square is minus 1 upon, we know that x plus iy into x minus iy is same as x square plus y square. Therefore 1 plus I into 1 minus I is same as 1 square plus 1 square, that is 1 plus 1. It means 2. Here plus 1 minus 1 cancel, minus I minus, that is minus twice I, 2 to cancel, that is equal to minus I. It means z equal to minus I. And therefore here x equal to 0, y equal to minus 1. And therefore r equal to root of x square plus y square. Value of x square is 0, value of y square is 1, that is root of 1. It means 1, that is r equal to 1. And theta equal to tan inverse of y upon x equal to tan inverse of value of y is minus 1 upon value of x is 0, that is minus 1 upon 0, that is minus infinity. And therefore value of theta nothing but 3 pi by 2. It means 270 degree. And therefore z equal to r in bracket cos theta plus I sin theta, but value of r is 1, value of theta is 3 pi by 2, and therefore z equal to cos of 3 pi by 2 plus I times sin 3 pi by 2 is complex number in polar form. These are examples we can express the complex number in polar form. Next type. If mod of z1 equal to mod of z2 equal to mod of z3, and z1 plus z2 plus z3 equal to 0, then prove that 1 upon z1 plus 1 upon z2 plus 1 upon z3 equal to 0. Here z1, z2, z3, three complex numbers are given. Their modulus is same and their addition is 0. Then we have to prove this 1 upon z1 plus 1 upon z2 plus 1 upon z3 equal to 0. Solution. First given that mod z1 equal to mod z2 equal to mod z3 and z1 plus z2 plus z3 equal to 0. And therefore 1 upon z1 plus 1 upon z2 plus 1 upon z3 equal to, first multiply and divide by first term by mod of z1 bar. Therefore z1 bar upon z1 into z1 bar. Multiply second term by mod of z2, multiply and divide by mod of z2 bar. Therefore z2 bar upon z2 into z2 bar. Similarly z3 bar upon z3 into z3 bar. But we know that z into z bar equal to mod z square. Therefore z1 into z1 bar is same as mod of z1 square. z2 into z2 bar is mod of z2 square. z3 into z3 bar is mod of z3 square. But mod of z1 equal to mod of z2 equal to mod of z3, and therefore z1 bar upon mod of z1 square plus z2 bar upon mod of z1 square plus z3 bar upon mod of z1 square, because their modulus is same. Now term of denominator is same and therefore equal to z1 bar plus z2 bar plus z3 bar is mod of z1 square. Now z1 bar plus z2 bar plus z3 bar is same as z1 plus z2 plus z3 whole bar. But z1 plus z2 plus z3 is 0 and therefore 0 bar is same as 0 and therefore 0 upon mod of z1 square, that is equal to 0. Therefore 1 upon z1 plus 1 upon z2 plus 1 upon z3 equal to 0 is required proof. Okay. Next example. If z equal to x plus iy is a complex number, then prove that mod of z minus 1 upon 1 minus z bar equal to 1. Solution. Let z equal to x plus I is complex number, and therefore mod of z equal to root of x square plus I square. To find the value of mod of z minus 1 upon 1 minus z bar, first you can find the value of z minus 1. Z minus 1 equal to z nothing but x plus iy minus 1, that is x minus 1 plus iy. And 1 minus z bar equal to 1 minus value of z bar is x minus iy, and therefore 1 minus x plus iy. And therefore mod of z minus 1 upon 1 minus z bar equal to mod of z minus 1 upon 1 minus z bar, but value of mod of z minus 1 nothing but z x minus root of x minus 1 bracket square plus y square, and mod of 1 minus z bar nothing but root of 1 minus x bracket square plus y square. And therefore we know that 1 minus x bracket square is same as x minus 1 bracket square, and therefore term of the numerator and denominator both terms are same and therefore equal to 1, and therefore mod of z minus 1 upon 1 minus z bar equal to 1. Okay, next example. Show that the locus of z will satisfy the condition mod of z minus 3 plus mod of z plus 3 equal to 4 represent a hyperbola. Solution. Let z equal to x plus iy be a complex number, and therefore mod of z minus 3 equal to x plus iy minus 3, and that is x minus 3 plus iy. Similarly, z plus 3 equal to z nothing but x plus iy plus 3, that is x plus 3 plus iy. And therefore mod of z minus 3 square nothing but square of real part plus square of imaginary part, that is x minus 3 bracket square plus y square. X minus 3 bracket square expansion is x square minus 6x plus 9, then plus y square. Also mod of z plus 3 bracket square nothing but x plus 3 bracket square plus y square. X plus 3 bracket square is x square plus 6x plus 9 plus y square. Now given that mod of z minus 3 plus mod of z plus 3 equal to 4, we can transfer the second term in right hand side. We get 4 minus mod of z plus 3, squaring on both sides. Left hand side is mod of z minus 3 square equal to right hand side bracket square expansion nothing but square of first term is 16, middle term minus 2 times their product plus square of second term. Therefore 16 minus 8 into mod z plus 3 plus mod of z plus 3 bracket square. And then we can substitute the value of mod of z minus 3 bracket square, value of z plus mod z plus 3 and mod z plus 3 bracket square. We get the value of mod z minus 3 bracket square is x square minus 6x plus 9 plus y square equal to 16 minus 8 into root mod of z plus 3 nothing but root of x square plus 6x plus 9 plus y square plus mod of z plus 3 brackets nothing but x square plus 6x plus 9 plus y square. Then left hand side x square, right hand x square cancel, 9 plus y square, this 9 plus y square cancel, left hand side remains only minus 6x, and therefore we get minus 6x equal to 16 minus 8 into root of x square plus 6x plus 9 plus y square plus 6x. We can transfer the 6x in left hand side, we get minus 12x. Also transfer 16 in left hand side, is minus 16 equal to minus 8 into root of x square plus 6x plus 9 plus y square. Changing this sign, therefore 12x plus 16 equal to 8 into root of x square plus 6x plus 9 plus y square. Dividing 4, we get 3x plus 4 equal to 2 into root of x square plus 6x plus 9 plus y square. Then squaring on both sides. The square of left hand side is 9x square plus 24x plus 16 equal to, here square of 2 is 4 into root cancel x square plus 6x plus 9 plus y square. Multiply each term by 4 separately. We get 4x square plus 24x plus 36 plus 4y square. Left hand side 24x, right hand side 24x cancel. 9x square minus 4x square nothing but 5x square. Transfer this minus 4x square in left hand side, that is minus 4y square. 36 minus 16, that is 20, and therefore 5x square minus 4y square equal to 20, which is equation of hyperbola, which is required answer. Next, if z is complex number and z minus 1 upon z plus I is purely imaginary, then we can find the locus of z. Solution. Let z equal to x plus iy be a complex number. First you can find the value of z minus 1 upon z plus I. Value of z is x plus iy minus 1 upon x plus iy plus I. First you can take x minus 1 plus iy upon x plus here iy plus I, taking I as common in bracket y plus 1. We can simplify this complex number by multiplying dividing by complex conjugate of denominator, that is multiply and divide by x minus I into y plus 1 upon x minus I into y plus 1. Simplify. We get x minus 1 into x minus x minus 1 into minus I into y plus 1, that is minus I into x minus 1 into y plus 1 plus iy into x, that is plus ixy, and last time value of I square is minus 1, therefore minus minus plus y into y plus 1. First you can take the real terms x into x minus 1 plus y into y plus 1. From the middle two terms you can take I as common. In denominator, x plus I into y plus 1 into x minus I into y plus 1 is same as x square plus y plus 1 bracket square. Then divide separately. You get x into x minus 1 plus y into y plus 1 upon x square plus y plus 1 bracket square plus I into xy minus x minus 1 into y plus 1 upon x square plus y plus 1 bracket square. Now, but given that z minus 1 upon z plus I is purely imaginary. Now this complex number is purely imaginary. It means real part of z minus 1 upon z plus I is 0. And therefore the real part nothing but x into x minus 1 plus y into y plus 1 upon x square plus y plus 1 bracket square equal to 0. Simplify. We get x into x minus 1 plus y into y plus 1 equal to 0. We get x square minus x plus y square plus y equal to 0. We can take x square minus x plus 1 upon 4, y square plus y plus 1 upon 4. We can add 1 upon 4 2 times in left hand side, also add in right hand side. And therefore x square minus x plus 1 upon 4 nothing but x minus 1 half bracket square. Y square y plus 1 upon 4 nothing but y plus 1 half bracket square. Right hand side is 1 upon 4 plus 1 upon 4 nothing but 2 upon 4. It means 1 half, that is 1 upon the root of 2 bracket square, which is required equation of the locus. These are examples of the complex number. Now, triangle equalities. We can prove some properties of complex number. First property, if z1 and z1 comma z2 are two complex number, then prove that mod of z1 plus z2 less than or equal to mod of z1 plus mod of z2. Proof. We can take complex number z1 and z2 in polar form. z1 equal to r1 in bracket cos theta 1 plus I sin theta 1 and z2 equal to r2 in bracket cos of theta 2 plus I times sin of theta 2. And there from this complex number, r1 is same as mod of z1, argument of z1 is same as theta 1. R2 is same as mod of z2 and argument of z2 is same as theta 2. And therefore we can find the value of z1 plus z2. Therefore z1 plus z2 equal to value of z1 is r1 in bracket cos theta 1 plus I sin theta 1 plus value of z2 is r2 in bracket cos of theta 2 plus I times sin theta 2. Multiply r1 separately, multiply by r2. Then first you can take the real terms, that is r1 cos theta 1 plus r2 cos of theta 2 plus I times r1 sin of theta 1 plus r2 sin of theta 2. And therefore mod of z1 plus z2 square nothing but square of real part plus square of imaginary part, that is r1 cos theta 1 plus r2 cos theta 2 bracket square plus r1 sin theta 1 plus r2 sin theta 2 bracket square. Taking the bracket square expansions, the square of first term, middle term 2 times their product plus square of second term, that is r1 square cos square theta 1 plus 2 times r1 r2 cos theta 1 cos theta 2 plus r2 square cos square theta 2. Similarly, bracket square expansion of second term is r1 square sin square theta 1 plus 2 times r1 r2 sin theta 1 sin theta 2 plus r2 square into sin square theta 2. Now this r1 square cos square theta 1 plus r1 square sin square theta 1. From the both term we can take r1 square as common. In bracket cos square theta 1 plus sin square theta 1, which is 1, and therefore simply r1 square. From this middle two terms you can take 2 times r1 r2 as common. In bracket cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. And from the last two term we can take r2 square as common in bracket cos square theta 2 plus sin square theta 2, its value is also 1, and therefore r2 square. And therefore mod of z1 plus z2 square equal to r1 square plus 2 times r1 r2 into, now this cos of theta 1 cos of theta 2 plus sin theta 1 sin theta 2, using trigonometric standard formula we get cos of theta 1 minus theta 2 plus r2 square. Now we know that for any angle theta, here cos of theta 1 minus theta 2 is always less than equal to 1, and r1 r2 both are positive, and therefore mod of z1 plus z2 square is less than equal to r1 square plus 2 times r1 r2 plus r2 square, because value of cos of theta 1 minus theta 2 is less than equal to 1. Therefore we can here less than equal to, we can value is here 1. Therefore 2 times r1 r2. The value of right hand side nothing but r1 plus r2 bracket square, and therefore mod of z1 plus z2 square is less than equal to r1 plus r2 bracket square, taking the square root. Therefore mod of z1 plus z2 less than equal to r1 plus r2. But r1 is same as mod of z1, r2 is same as mod of z2, and therefore mod of z1 plus z2 less than equal to mod z1 plus mod of z2. This first property of the complex number. Second, if z1 and z2 are two complex number, then prove that mod of z1 minus z2 greater than equal to mod of z1 minus mod of z2. Proof that we can take z1 and z2 are two complex number in polar form, that is r1 cos theta 1 plus I times sin theta 1, and z2 is r2 into cos of theta 2 plus I times sin of theta 2. Therefore here also r1 is same as mod of z1, argument of z1 is theta 1, r2 is same as mod of j2, and our argument of j2 nothing but theta 2. Here first you can find the value of z1 minus j2, and therefore z1 minus j2 equal to first value of z1 minus value of j2. Simplify, we get z1 minus z2 equal to r1 cos theta 1 minus r2 cos theta 2 plus imaginary part I in bracket r1 sin theta 1 minus r2 sin theta 2, and therefore mod of z1 minus z2 square equal to square of real part plus square of imaginary part, that is cos r1 cos theta 1 bracket minus r2 cos theta 2 bracket square plus r1 sin theta 1 minus r2 sin theta 2 bracket square, taking the bracket square expansion, and therefore r1 square cos square theta 1 middle term minus 2 times r1 r2 cos theta 1 cos theta 2 plus r2 square cos square theta 2 is bracket square expansion of first term. Then bracket square expansion of second term r1 square sin square theta 1 middle term minus 2 times r1 r2 sin theta 1 sin theta 2 plus r2 square sin square theta 2. From this 2 term we can take r1 square as common. We get in bracket cos square theta 1 plus sin square theta 1, its value is 1, that is first term is r1 square. From this middle 2 term we can take minus 2 times r1 r2 as common, in bracket cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. Here we can take r2 square as common, cos square theta 2 plus sin square theta 2, its value is 1, therefore last term is r2 square. Now this cos theta 1 cos theta 2 plus sin theta 1 sin theta 2, value of this bracket term is cos of theta 1 minus theta 2, and therefore mod of z1 minus z2 square equal to r1 square minus 2 times r1 r2 cos of theta 1 minus theta 2 plus r2 square. Now we know that the value of cos of theta 1 minus theta 2 is less than equal to 1, and r1 r2 both are positive, and therefore mod of z1 minus z2 square is greater than equal to r1 square minus 2 times r1 r2 plus r2 square. Here value of cos of theta 1 minus theta 2 is less than equal to 1. It means minus cos of theta 1 minus theta 2 greater than equal to minus 1 here. Therefore r1 square minus 2 times r1 r2 plus r2 square, the value of the right hand side nothing but r1 minus r2 bracket square. Taking the positive square root, we get mod of z1 minus z2 greater than equal to mod of r1 minus r2. We can take only positive root, that is mod of r1 minus r2. But r1 is same as mod of z1, r2 is same as mod of z2. Therefore mod of z1 minus z2 greater than equal to mod of z1 minus mod of z2. This second property of complex number. Third, if z1 and z2 are two complex number, then prove that mod of z1 into z2 equal to mod z1 into mod z2, and argument of z1 into z2 equal to argument of z1 plus argument of z2. Proof. Similarly, we can take here two complex numbers Z1 and Z2 in polar form. Z1 equal to R1 cos theta 1 plus I sin theta 1, and Z2 equal to R2 in bracket cos of theta 2 plus I times sin theta 2. Here also R1 is same as mod Z1, argument of Z1 equal to theta 1. R2 is same as mod of Z2, argument of Z2 is same as theta 2. Here you can find Z1 into Z2, it means taking their product. Z1 into Z2 equal to this is value of Z1 into value of Z2, and therefore R1 R2 into cos theta 1 plus I sin theta 1 into cos of theta 2 plus I times sin theta 2. Taking the product, we get Z1 Z2 equal to R1 into R2 in bracket cos theta 1 into cos theta 2 plus I times cos theta 1 into sin theta 2 plus I times sin theta 1 into cos theta 2. Last term I sin theta 1 into I sin theta 2, value of I square is minus 1, that is minus sin theta 1 into sin theta 2. We can take first real part, the first term and last term, that is cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. From the middle two terms we can take I as common, and therefore Z1 into Z2 equal to R1 into R2 into this cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 is same as cos of theta 1 plus theta 2, cos A plus B formula, plus value of sin theta 1 into cos theta 2 plus cos theta 1 into sin of theta 2 is same as sin of theta 1 plus theta 2, and therefore from this complex number we get mod of Z1 into Z2 is same as R1 into R2, and argument of Z1 into Z2 is same as theta 1 plus theta 2, and therefore mod of Z1 into Z2 equal to R1 is same as mod of Z1, R2 is same as mod of Z2, and argument of Z1 into Z2 equal to theta 1 is same as argument of Z1 plus theta 2 is same as argument of Z2. This third property of the complex number. Next, if Z1 comma Z2 are two complex number, then prove that mod of Z1 upon Z2 equal to mod of Z1 upon mod of Z2, and argument of Z1 upon Z2 equal to argument of Z1 minus argument of Z2. Proof. Let Z1 equal to R1 in bracket cos theta 1 plus I sin theta 1. Z2 equal to R2 in bracket cos of theta 2 plus I times sin theta 2. These two complex number in polar form, and therefore mod of Z1 is same as R1, argument of Z1 equal to theta 1, mod of Z2 is same as R2, and argument of Z2 equal to theta 2. Here you can find the value of Z1 upon Z2. Value of Z1 is R1 in bracket cos theta 1 plus I sin theta 1. Z2 is R2 in bracket cos theta 2 plus I times sin theta 2. To simplify this complex number, we can multiply and divide by complex conjugate of denominator, that is cos of theta 2 minus I times sin of theta 2. And therefore, we can simplify Z1 upon Z2 equal to R1 into taking the product cos theta 1 into cos theta 2 minus I times cos theta 1 into sin theta 2 plus I times sin theta 1 into cos of theta 2, last term minus minus plus sin theta 1 into sin theta 2. The value of I square is minus 1, therefore minus minus last term is plus term, upon cos of theta 2 plus I times sin theta 2 into cos of theta 2 minus I times sin of theta 2, nothing but square of real part plus square of imaginary part, that is sin square cos square theta 2 plus sin square theta 2. But value of cos square theta 2 plus sin square theta 2 is 1, and therefore denominator is only R2. Here R1 into, first you can take real term cos of theta 1 cos of theta 2, last term plus times sin of theta 1 sin theta 2. From the middle term we can I as common, sin theta 1 into cos of theta 2 minus cos of theta 1 into sin of theta 2, and therefore we get Z1 upon Z2. But this cos theta 1 cos theta 2 plus sin theta 1 sin theta 2, using trigonometric formula, value of this term is cos of theta 1 minus theta 2, and sin theta 1 into cos of theta 2 minus cos of theta 1 into sin of theta 2 is nothing but sin of theta 1 minus theta 2, and this value of Z1 upon Z2 equal to R1 upon R2 into cos theta 1 minus theta 2 plus I times sin of theta 1 minus theta 2, and therefore mod of Z1 upon Z2 equal to R1 upon R2, and argument of Z1 upon Z2 equal to theta 1 minus theta 2. And therefore mod of Z1 upon Z2 equal to R1 is same as mod of Z1 upon R2 is same as mod of Z2. Therefore mod of Z1 upon Z2 equal to mod of Z1 upon mod of Z2, and argument of z1 upon z2 equal to theta 1 minus theta 2. Theta 1 is same as argument of z1 minus theta 2 is same as argument of z2, and therefore argument of z1 upon z2 equal to argument of z1 minus argument of z2. These are the properties of the complex number. Next, if z1 comma z2 are two complex number, then prove that mod of z1 plus z2 square plus mod of z1 minus z2 square equal to 2 times mod of z1 square plus 2 times mod of z2 square. Solution. Let you can take z1 z2 to complex number in polar form. First we can find the value of z1 plus z2. This value of z1 plus this value of z2. Therefore, r1 cos of theta 1 plus r2 cos of theta 2 plus I times r1 sin theta 1 plus r2 sin of theta 2. And therefore, mod of z1 plus z2 square equal to the square of a real part plus square of imaginary part, that is r1 cos theta 1 plus r2 cos of theta 2 bracket square plus r1 sin theta 1 plus r2 sin theta 2 bracket square. Taking the bracket square expansion, we get r1 square cos square theta 1 plus 2 times r1 r2 cos theta 1 cos theta 2 plus square of second term is r2 square cos square theta 2. Similarly, we can take bracket square expansion of this second bracket term. Now, from this two term we can take r1 square as common. In bracket cos square theta 1 plus sin square theta 1, but its value is 1, and therefore addition of these two terms is simply r1 square. From this middle two term we can take 2 times r1 r2 as common. In bracket cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 plus from the last two we can take r2 square as common. In bracket cos square theta 2 plus sin square theta 2, its value is also 1, therefore last term is r2 square, and therefore mod of z1 plus z2 square equal to r1 square plus 2 times r1 r2. The value of this bracket term cos theta 1 into cos theta 2 plus sin theta 1 into sin of theta 2 is same as cos of theta 1 minus theta 2 plus r2 square. This value of mod of z1 plus z2 square. Similarly, we can find the value of mod of z1 minus z2 square. This mod of z1 minus z2 square is same as r1 square minus 2 times r1 r2 cos of theta 1 minus theta 2 plus r2 square, and therefore mod of z1 plus z2 square plus mod of z1 minus z2 square equal to value of mod of z1 plus z2 square is r1 square plus 2 times r1 r2 cos of theta 1 minus theta 2 plus r2 square plus value of mod of z1 minus z2 square is r1 square minus 2 times r1 r2 cos of theta 1 minus theta 2 plus r2 square. This term is plus minus this term cancel. r1 square plus r1 square we get 2r1 square, r2 square plus r2 square nothing but 2r2 square. And therefore mod of z1 plus z2 square plus mod of z1 minus z2 square equal to 2r1 square plus 2r2 square. But r1 is same as mod of z1, therefore r1 square is same as mod of z1 square and r2 square is same as mod of z2 square, and therefore mod of z1 plus z2 square plus mod of z1 minus z2 square equal to 2 times mod of z1 square plus 2 times mod of z2 square, which is required proof. These are properties of complex number. Then we can summarize. Now, for z equal to x plus I is complex number. The complex conjugate of complex number z nothing but z bar, which is nothing but x minus iy. If z equal to x plus iy is complex number, the modulus of z nothing but mod of z, and value of mod of z nothing but a root of x square plus y square, that is square of real part plus square of imaginary part. Then from this z into z bar we can prove the result. Z into z bar is same as mod of z square. Now if z equal to x plus iy, z bar equal to x minus iy, therefore z plus z bar is nothing but twice x, z minus z bar equal to 2iy. Then the z equal to x plus y, this form of complex number nothing but complex number in Cartesian form. Z equal to r in bracket cos of theta plus I times sin of theta is another form of complex number. This form nothing but complex number in polar form. And z equal to r into e raised to I theta, this complex number in exponential form. Therefore, these three forms of complex number: Cartesian form, polar form, and exponential form. Now, modulus of z is same as mod of z equal to r equal to root of x square plus y square, and amplitude of z nothing but AMP in bracket Z equal to theta equal to tan inverse of y upon x. It is also called as argument of Z. And therefore R equal to root of x square plus y square and theta equal to tan inverse of y upon x. These are relation between Cartesian and polar coordinate. Now we know that I nothing but root of minus 1, and therefore value of I square is minus 1, value of I cube is minus I, value of I raised to 4 is 1, and value of 1 upon I is minus I. These are some standard conditions of the complex number. Then properties. There are 5 properties. If Z1 and Z2 are two complex numbers, then we have proved mod of Z1 plus Z2 is less than equal to mod of Z1 plus mod of Z2. Second, mod of Z1 minus Z2 greater than equal to mod of Z1 minus mod of Z2. Third is mod of Z1 into Z2 equal to mod Z1 into mod Z2, and argument of Z1 into Z2 equal to argument of Z1 plus argument of Z2. Fourth, mod of Z1 upon Z2 equal to mod of Z1 upon mod of Z2, and argument of Z1 upon Z2 equal to argument of Z1 minus argument of Z2. And last, mod of Z1 plus Z2 square plus mod of Z1 minus Z2 square equal to 2 times mod of Z1 square plus 2 times mod of Z2 square. These are the 5 properties of the complex number Z1 and Z2. Thank you. Thank you for your attention. Please like and share this video and subscribe my YouTube channel Parishram Maths Academy. Thank you.